Hello everyone, we will be presenting our paper on hierarchical learning and control for in-hand micromanipulation using multiple laser-driven micro tools. While much progress has been made for robot manipulators, people are thinking if we can realize Dexterous in-hand manipulation at a macro scale. However, the high degrees of freedom, the uncertain dynamic model, and Brownian perturbations bring challenges to this problem. Compared with a multi-fingered robot hand, existing micromanipulation with laser-driven tools succeed in only simple tasks, such as grasping and caging. Moreover, model-based control methods are commonly used, reducing the dexterity of the robotic system. So our goal is to develop a new micromanipulation system composed of multiple laser-driven micro tools to demonstrate the feasibility of in-hand manipulation at a macro scale. Let's come to the problem statement. The basic principle of optical tweezer is here. A highly focused laser beam can exert force on a macro object and hence stably trap it. The force follows a Gaussian distribution. The right picture shows the typical structure of the optical tweezer. We can see that there are really two ways to manipulate the object. The first is to move the laser source directly, and the second is to fix the laser beam while moving the motorized stage. In this slide, we consider the formulation of indirect manipulation. A series of microbeams with uncertain dynamic parameters are trapped by the laser beam and then controlled to interact with the target object. The overall hierarchical structure is shown on this slide. At the low level, we use two adaptive control methods to control both the motorized stage and the laser beam. Firstly, the laser traps the microbeams and then use them as a tool to form a pre-grasping. At the high level, a reinforcement learning-based planning approach is proposed to coordinate the contact point and moving trajectory of the microbeams, and then to manipulate an uncertain target object. In the trapping phase, we denote U as the input torque of the stage model and Q as the position of the laser beam. Then an adaptive slide mode control method is implemented here to trap the beams sequentially by driving the motorized stage. After all the beams are trapped by the laser beams, they are employed as laser-driven micro tools to formulate the pre-grasp. The dynamic model of single micro tool is represented here, and the control input P specifies the relation position of laser beam. The same adaptive technique is developed here by adding the same control term to deal with the interaction force. Therefore, the micro tools can move simultaneously to formulate the pre-grasp. The reference trajectory for the proposed adaptive control screen is generated from the planning model at a high level. Note that in-hand micromanipulation is a hybrid planning problem with high degrees of freedom and various constraints, which is challenging for the model-based method. Hence, we model this problem as a Markov decision process and introduce a deep reinforcement learning approach to carry out this task with PPO algorithm. The goal of the agents is set as moving and rotating the target micro-object from a random initial position. The state is defined in vision space consisting of the micro tool's position and the pose of the micro-object. The action is regarded as a differential position with respect to the object center. And we also propose downstream works to provide rich exploration. Let's come to the results. We first validate the proposed adaptive controller for the trapping and pre-grasping tasks in MATLAB and Simulink. The GIF shows 4 microbeams away from the laser beams at the beginning. Then the motorized stage is activated such that the laser beams move to trap the beams. After that, the beams are used as micro tools to generate a damage shift pre-grasp form. Since the errors are all converged to 0, the proposed controller can carry out these tasks efficiently. Then we validate the proposed hierarchical learning and control scheme for the in-hand manipulation in PyBullet. The unmodeled interaction force and dynamic uncertainty are considered. For compression, end-to-end learning and formation control methods are also implemented. As shown in Table 4 and Table 5, our method is more robust and simply efficiently than other methods. This slide shows that our method could relocate the object to the design configuration from a random initial point and is applicable to different shapes. And this slide shows that our method is more robust and simply efficiently than other methods. The whole manipulation process are shown on this slide, containing trapping, pre-grasping, and in-hand manipulation. Future works will be devoted to real-world experiments. Thank you.